In the second part of this week's lecture, we will go over the synthetic or gravity models that are used in trip distribution modeling. Gravity models are generated from an analogy with Newton's gravitational law, and it states that the number of trips going from I to j is equal to a proportionality factor multiplied by the population of zone I multiplied by the population of zone j divided by a square of the distance between I and j. However, this is too simplistic. Further generalization of the gravity distribution model can be obtained by assuming that the effective distance could be better modeled by a decreasing function of distance or travel time or travel cost between the zones. Therefore, Tij, number of trips going from I to j, can be estimated by a proportionality factor multiplied by OI, which is the number of trips produced at zone I, D multiplied by dj, number of trips attracted at zone j, multiplied by a generalized function of the travel cost. This generalized function of travel cost is also known as deterrence function because it represents the disincentive to travel as distance or time or cost increases. There are different forms for deterrence function. You can consider an exponential function or a power function or a combined exponential and power function. But how are these different? Here is a visual comparison of different examples of different deterrence functions and how they look like. For example, consider an exponential function with parameter beta minus 0.01. So this is the exponential form we are looking here. And compare this with the red curve and the purple curve. They're all of these three are exponential deterrence functions with a different beta. And you can see how changing the beta would make the curve different. As travel cost increases, there's a decreasing trend in all of these deterrence function curves, but there is a slight difference in the beginning of the curves where the travel cost is not yet very high. Similar to the gross factor model, the synthetic or gravity model can be applied either as singly constrained or doubly constrained. To do so, we will incorporate the proportionality factor into variables ai and bj. So if I go back to the original gravity distribution model, where we had the proportionality factor multiplied by OI dj and then FCIJ, we change this alpha and replace it with capital AI and capital BJ. And later, we combined AI and OI with a small ai and BJ and DJ with a small bj. So the gravity model can be represented as the number of trips going between I and j is equal to balancing factors AI and BJ multiplied by OI dj and the deterrence function. To apply this to an actual trap distribution modeling problem, we need to apply a similar iterative process to estimate Tij, very similar to the gross factor model implementation as we saw earlier. For either origin or destination constraint, we can make balancing factors ai or bj equal to 1. For example, if we want to implement it as an origin constraint model, we assume bj is equal to 1 for all the j's, and we calculate the balancing factor ai as equal to 1 over the sum of the dj's multiply the deterrence function over all j's. For a doubly constraint implementation, we need to calculate both the balancing factors separately. ai would be equal to 1 over the sum of the bj dj multiplied by deterrence function over all j's, and bj's similarly would be 1 over the sum of the ai oi multiplied by the deterrence function summed over all the i's. So in fact, this singly constraint implementation is a special case of a doubly constrained model, where if you look at this AI formula, if we replace this bj by 1, we get the same formula as above. To better understand how these formulas are going to be used, how you can implement a singly or doubly constrained gravity model in a trip distribution modeling problem, please have a look at activity 5.4. In this activity, we will go over example 5.4 from the textbook. It is useful to illustrate the gravity model with an example related to the problem of expanding a trip matrix. Consider a cost matrix as represented in table 5.8, where we have the travel cost in minutes between each OD pairs. And we also have the target productions and target attractions estimated from a trip generation model. The gravity model is expressed as Tij equal to AIBJ multiplied by a deterrence function, which the deterrence function is expressed as an exponential function. If we assume beta in the deterrence function is equal to 0.1, we can convert this cost matrix to a deterrence function matrix with simply replacing beta with 0.1 and Cij, which is the cost of travel between each origin destination pairs, and we get this new matrix of deterrence. The good thing about the gravity model, unlike the gross factor method, is that we do not need a origin destination demand matrix for the base year. We can simply calculate the travel number of trips between I and j for the future by using this deterrence function cost matrix and the total number of productions of the target year and total number of attractions in the target year. I now switch to an Excel file to show you how these values are actually being calculated. So here I have the cost matrix, the travel cost between each origin and destination pair expressed as minutes, using the deterrence function, the exponential format determined by the problem. I calculate this new deterrence function matrix, where each cell is basically using the exponential function as expressed by the problem and the estimated beta, or better to say assumed beta by the problem, multiplied by the each cell of the cost matrix. So we calculate this as an exponential of minus 0.1 multiplied by Cij. So you calculate the deterrence function for each cell accordingly to get the entire matrix of deterrence function. The problem also gave us the total number of production for each zone and total number of attractions for each zone in the future year. So the first step to implement a doubly constrained gravity model is to calculate Tij. So we specify a matrix for Tij. We have the total productions and total attractions, which is the sum of the columns and sum of the rows. But how do we get this Tij? So the formula of the Tij, if you remember from the slides, was AI multiplied by OI multiplied by BJ multiplied by DJ multiplied by the deterrence function FCij. So for each cell, we need to calculate this AI and BJ. What is the OI? OI would be O1, which is 400 in this case. What about DJ? J is also 1 for this cell. It's going to be 260. But what is AI and BJ? For the first iteration in a doubly constrained implementation, we assume BJ equal to 1 and we calculate AI given the formula we had in the slide, which was 1 over the sum of the DJ, BJ, FCij. So we calculate the sum of the DJ, BJ, FCij here, which is shown here in the Excel file. So we multiply 260 by 0.74, 400 by 0.33, 500 by 0.17, 802 multiplied by 0.11, and we sum this to get this summation value. Then AI was 1 over this summation value, so it would be 1 over this cell. We get the AI. We do similarly for the other origins. So we calculate the sum of the dj, bj, fcij for another originating zone. It would be 260 multiplied by 0.3, 400 multiplied by 74, and so on to calculate this. And similarly, we get the AI. After we have all the AIs for each originating zone, we can now calculate this Tij, where, for example, for this cell, it would be AI, which is 0.002, multiplied by OI, which is 400, multiplied by BJ, which is assumed to be 1, multiplied by DJ, which is 260, multiplied by FCIJ from the deterrence function matrix, which is 0.74. So we get this cell value here. If I go into another cell for another another example, let's have a look at this. So this cell will be calculated as A3, which is 0.0012, multiplied by OI, which is O3, multiplied by 400, multiplied by BJ, which is assumed to be 1 in the first iteration, multiplied by DJ, which is D3, 500, multiplied by FCIJ, which comes from this table. And if you continue calculating these values for the entire table, you get this trip matrix. And you can now sum the total productions, as I've shown here, for each row, and sum of the attractions for the columns, and as I've shown here. And you can see, because in the first iteration we assumed bj to be equal to 1, what we are actually doing is like applying a origin-based constraint model for the first iteration. That's why the total productions are equal to the target productions with no error, while the attractions are a little bit off. So in the next iteration, we try to reduce the error here. So in the second iteration, we need to again fill this table. How to do it? We use the Tij formula. To do so, we need to calculate AI and BJ, very similar to the previous iteration. However, this time, we don't need to assume BJ equal to 1. We already have AIs. This time, we calculate BJs. So BJ was the sum of 1 over summation of OI, AI, FCIJ. So we calculate this summation for each of the J's. So here would be O1 multiplied by A1 multiplied by FC11. So it would be O1 multiplied by the O1 multiplied by the value from the deterrence function matrix. And if you continue calculating that, you get the value for the summation, then Bj would be 1 over this summed value. Remember, to calculate this value, AI is coming from the previous iteration. After we calculate all the BJs, we can now get the new Tijs. So for example, this one, it would be T12 is equal to A1 multiplied by O1 multiplied by B2 here, multiplied by D2 here, multiplied by FCIJ, which is FC12, which comes from the deterrence function table here. So that's how we get this table. So we continue that and we get all the cells here. Now let's have a look at the total productions and attractions. In the second iterations, the total attractions will match the target attractions, so there will be no error here. But the total productions will be a little off with some error. So we continue the iterations and we calculate again AIs. Remember, bj comes from the previous iteration. You see the errors are going down. We do it for another iteration. Again, we calculate bj's ai coming from the previous iteration, where the error is actually pretty small. And that's where we probably are reaching convergence, and that's where we stop the iterative process. With this level of errors, I'm happy, therefore I accept this Tij values, which are the output of the trip distribution model. So what I would like you guys now to do is to go over this example again, try to create a similar spreadsheet for yourself. Try to formulate all these formulas by yourself so you learn. If you just follow what I did here, you should be able to create an Excel file for yourself. What is confusing a little bit for most of the people who learn this method first is the calculation of the AI and BJs at the beginning. So make sure you pay enough attention how I have calculated them. Try to reformulate and recreate this on your own by yourself so you learn. The Tij calculation is relatively easy, but the confusion comes from where the I and J's come from. So you need to be careful when you formulate this cell that AI is coming from, what cell BJ is coming from, what cell, and about the OI and DJ similarly. So please go ahead and do this on yourself. The last method that I would like to briefly introduce to you guys is the destination choice modeling. Destination choice modeling is a generalization of the traditional gravity model that we just went over. This is an advanced approach that uses discrete choice modeling theory. This method will provide a better behavioral basis for trip distribution instead of using some simplistic gravity model. We use some behavioral modeling perspective using discrete choice theory. We will cover some topics on discrete choice modeling in a few weeks from now,